Hi. Okay, so I'm gonna explain exercise 2 on section 25 to 26. I'll just do 2c. So the function is f of z equals e to the y e to the ix, and we're supposed to show that it's not analytic anywhere. So if we expand e to the y e to the ix, the e to the ix we just use Euler's identity. So then we'd expand that, we get e to the y cosine x plus I e to the y sine x. So then u is e to the y cosine x, and then v is e to the y sine x. So then the partial derivatives are ux equals negative e to the y sine x, and then vy equals e to the y sine x. So basically, if we want the Cauchy-Riemann equation ux equals vy to hold, then we need to have sine x equals 0. So if we have sine x equals 0, then we have to have that x equals like k pi. It has to be like a multiple of pi, basically. So for the other Cauchy-Riemann equation, uy equals negative vx, it turns out we have to have uh, cosine x equals 0 because we have e to the y cosine x equals negative e to the y cosine x. So we need cosine x equals 0. So then x has to be equal to pi over 2 plus k pi. So x has to be a multiple of pi, but it also has to be like, I guess it's just a multiple of pi over 2 plus some multiple of pi. But it turns out it can't be both of those because if we had k1 pi equals pi over 2 plus k2 pi, then we get a contradiction. K1 minus k2 equals 1/2. So basically, if you try to solve the Cauchy-Riemann equations, they just never solve. So basically, it's not differentiable. That proves that it's definitely not differentiable anywhere, so it can't be analytic.